Welcome Dika P Sogong aboard. Your learning journey starts now. Ever felt like some problems are just easier to check than to solve? That's the heart of P versus NP. It's not just an academic puzzle, it's a million-dollar question, literally. So, what's the deal? So, NP isn't just about finding a needle in a haystack. It's more like knowing if there's a needle in the haystack without necessarily digging through every single stalk. We call this existential projection. You have your input X, and you're looking for a certificate W that makes a relation R true. If such a W exists, X is in your language L. The verification process gets both X and W. But the decision problem, it only gets X. It has to figure out if that certificate fiber W sub R of X is empty or not based on X alone. The big question is, can we do this efficiently without checking every possible W? That's where the real fun begins. Now, here's a common trap, thinking that because the number of potential certificates is finite, we can just list them all. Well, technically, yes. For any given instance, you could eventually find the answer by checking every possible certificate. This satisfies basic normalization conditions, let's call them U1 to U8. But here's the catch, that exhaustive search is usually exponential. It might terminate, but it won't be efficient. To bridge the gap to P versus NP, we need stronger conditions, C1 through C8. These demand uniform polynomial resources, construction, steps, state size, everything must scale nicely with the input size. Just having a finite process isn't enough. It needs to be fast and uniform. Without these, we're stuck in the land of potentially very long searches. Okay, so we need polynomial resources. Can we prove lower bounds? Yes, but only for specific types of algorithms. Consider local provenance preserving normalizers sync systems that build proofs or solutions by combining small local pieces like clauses in resolution. For tricky Cyton formulas built on expander graphs, known results show that any resolution proof needs to get exponentially wide. This translates directly into an exponential lower bound for these kinds of local semantic normalizers. It's a solid result showing genuine incompressibility in this restricted setting. However, this doesn't automatically mean P is not equal to NP overall. Why? Because clever global methods like Gaussian elimination for X or Z can bypass these local limitations entirely. So this is progress, but it's not the final word. So how do we get from these restricted lower bounds to the grand P versus NP statement? The report proposes a crucial bridge, the General Context Stable Incompressibility Principle, or GSC. The idea is quite profound. If we can show that for 3 there's no way to create a uniform polynomial time constructible summary or quotient that faithfully represents all possible context and still captures the solution, then P cannot equal NP. Think of it as proving that the semantic information loss from projection is fundamentally irrecoverable via any efficient context-aware compression. If GSC holds true and assuming compilation conditions C1 to C8 hold, then boom, P is not equal to NP. But here's the kicker, GSC itself is still unproven. It's the missing piece, the final frontier in this approach. So, wrapping it up, P versus NP isn't just about whether you can find a solution. It's about whether you can summarize the entire search space, considering all future possibilities, into a compact, efficient representation. The journey moves from simple finite processes to demanding uniform polynomial resources and finally hinges on proving that universal semantic compression is impossible for hard problems like 3ASAT. That's the challenge, and that's where the research continues.